Welcome to section 10.7. Here we're going to look at how to solve systems of nonlinear equations. And so you've solved systems of equations before, either through substitution or elimination, and we want to use those same skills here. There's really no difference between how we solve them, except in the number of solutions. And so what he wants you to realize first is, instead of two lines intersecting, which can intersect, as you know, in one place, no places, right, because they're parallel, or in an infinite number of places because they're the same line. There's just three outcomes. If we have two different shapes, kind of like the first one, a parabola mixed with a line, they can intersect in two places. They cannot intersect at all. They could totally intersect in one place, right? So there's lots of options that are there. I think that may be it, actually. A circle and a line, right? Two places that they could intersect, one place if it's tangent, no places. A hyperbola and a line, right? What could that look like? Something like that, right? So there's ways that things can interact. A parabola and a parabola, right? They could intersect in a couple places as well. An ellipse and a hyperbola could intersect as many as four places, right? If I drew the ellipse in there, right? Looks like a baseball. That's pretty cool. An ellipse and an ellipse could intersect in four places as well. And so you may end up with one solution, no solutions, two solutions, four solutions, and they all work out just fine, right? He's showing pictures of them down here. I apologize. I didn't need to do all of that. I just scrolled down. I didn't realize that. So we've solved systems of linear equations in the past, right, by finding out where they intersect by doing substitution or elimination, and we'd find out, oh, that's where they intersect. We're going to do the same thing, right? I don't think you need to be reviewed over substitution elimination because you've used those so much in your previous experiences, both in Algebra 1 and in Algebra 2, in beginning and intermediate algebra it's taught. So what's happening in something like this? So if we look at a situation like this, let's just read this. After I find the values for one variable, how do I find the values for the other variable? So if we take a look at something like this one would be nicely done through substitution. He's going to substitute this second equation into the first. He's going to say, I know the y's in the second equation have to be like x minus 2. So I'm going to substitute those in. And when he does, he gets x is equal to x minus 2 squared. He's careful to bring over his x, talk about factors of 4 that add to be 5, 4 and 1. Both would be subtracted in the factorization, so we get 4 and 1. So now we're going to plug in, and it says, does it matter where you substitute in for? And he's saying, yeah, it may matter. So if you substitute the 4 or the 1 into the relation with the smallest exponent, then you would get 4, 2, and 1, negative 1. So which is the one with the smallest exponent? This y equals x minus 2. So he's using that, and he gets those two solutions. If you substitute it into the one with the larger one, then you get a couple of other solutions. The solutions are not the same in both cases, so what's happening? If we check the two solutions obtained by plugging in the first degree equation to see if it also works in the second, we see that they both work. If we check the four solutions obtained by plugging the second degree equation to see if they also work in the other one, we see that the extra ones don't work. And so what do we learn from this? He's saying it's all about a one-to-one relationship that the line has. Every x is mapped to a single y, and so therefore it's not true that x is equal to y squared. Well, for x is equal to y squared is not one-to-one, right? And so therefore, so how do I find the actual solutions? If you have a one-to-one function relation that is not one-to-one, find the solutions to the one-to-one and check them in the other relation. This is the most common approach. In most cases, it means using the linear function to find the solutions and check them in the other function. Okay, so we'll watch this happen. He's making it sound like making it a little bit more complicated than it needs to be, maybe, but we'll try it out. So here we got y is equal to x squared and y is equal to negative x squared plus 8. And so we're going to substitute negative x squared plus 8 into the y equals x squared. So this is a very nice way to do it. Both of these are solved for y, and so what we want to do is force the two systems to be the same. So he's saying we're substituting this one into here, and that's true, or it could be looked at the other way around. And so if we set those two equal to each other, then we get 2x squared minus 8, right? Adding the x squared over, subtracting the 8 over, we get 2x squared minus 8 equals 0. We can pull out the 2 and it factors, and so our two solutions for x are 2 and negative 2. We're going to substitute the 2 or negative 2 into the y equals x squared equation because that's the easiest one there is. Both of these are not one-to-one. They're both parabolas. And so as we substitute the 2 in, we get a 4 out. As we substitute the negative 2 in, we also get a 4 out. And so one of these should be positive 2. So one of the solutions is 2, 4. The other one is negative 2, 4. And we're finished. And two parabolas can't intersect in more than two places, so you don't have to worry that you're missing a solution at all. Here we have a parabola with a line. And so again, we're going to set these y values equal. Substitution is a great way to go about this and used often. So we have a fraction, so he's going to double everything. So he's setting the two equal to each other right here. Then he's going to multiply everything by 2 to get rid of the fraction. So we should see a doubling of everything, and it looks perfect. We are going to get everything to one side. So we got the 2x squared. We're going to add 10, and that's where the negative 20 is coming from. We're going to subtract x, and that's where the 3 is coming from. You know how to factor. We're not worried about your factoring. You can see that it's a 2x minus 5 and an x plus 4. You can see that we would get an 8 and a negative 5, which does produce a 3, so we're good. So the two solutions are 5 halves or negative 4 coming out of that. Now what he's suggesting, all that big stuff set up there, is if you have something that's one-to-one, something where the variables are not squared, which we do, if you have a line, go ahead and use the line, because the one-to-one nature will limit our solutions. And so all we're doing is plugging in. We're plugging in the negative 4, and we're getting negative 2 minus 5 for negative 7, so negative 4, 7 is the solution. We're going to plug in the 5 halves and get 5 fourths minus 20 fourths. And 20 minus 5, like you know, is 15 fourths. Your fraction work needs to be good. If you're worried about fractions, you picked the wrong majors. So if you're worried about trig fractions, you picked the wrong majors because we do a lot of them. So, and calculators make it worse, so not better. So be careful in that. So we get two solutions out of that. So pretty fun coming through. Again, we're just going to set the two equal to each other because the y's are solved for. We're going to get that. And oddly enough, he picked something where it didn't work out super nice, but those are the solutions, right? So what do we get out of this? We get a negative 3 out of this. So we were kind of saved. We'd have a ugly work. It's really ugly if that wasn't a negative in there. So you're wondering, how are you going to run across a no solution? Easy. The no solutions come out when what you come up with can't happen, like an x squared equals a negative. And in this case, you can't have a negative underneath the radical. So if we backtrack, he's setting the two equal to one another. Let's just make sure everything was done right. We subtract the x squared, we subtract the 2x, we subtract the 3, everything's perfect. X is equal to negative b plus or minus b squared minus 4 times 1 times 1. Yep. And so there's no solution. So these parabolas, he's showing you what they look like graphed. They're inside one another, where the outside one is more wide. The green one is more wide than the blue one. So they'll never touch. Okay. And then now we have a circle and a line. So again, we're going to take a look at this, figure out how to substitute in. Could do elimination, but probably easiest to substitute. Be very careful. So they're going to take this line and substitute it in. And you know in the end we're going to use the line, right? We're going to use the line because the line's a one-to-one function. That's what he was trying to say in the beginning. So we're going to plug in that negative x minus 3 there and square it into this equation, so it's getting dropped right in there. So this guy's hanging out, the x squared, that's 17, but negative x times negative x is x squared. Positive 3x is a 9x, and negative 3 is a positive 9. So that all looks perfect. 2x squared, 6x hanging out, and the 17 coming over for, yes, a negative 8. Can pull a 2 out and be left with that. Factors of 4 that subtract to be 3 are 4 and negative 1. And so there we go. Negative 4 and 1 we have to plug in, and so we use the line. Negative of negative 4 plus 3 is 1, so 4, 1 is a point of intersection. I'm sorry, negative 4, 1. And we plug in the 1 and get negative 1 minus 3 for negative 4, and 1 minus 4 is a point of intersection. And then he used a graphing utility to show you where those were. Awesome. So, and then a hyperbola. You may not know that that's a hyperbola. Kind of park that in your memory. That's a hyperbola, not in its standard form, but in a general form. Take a look. If you solve for y, it's 1 over x. Here's the reason why it's a hyperbola. You know what the 1 over x graph looks like potentially from your intermediate algebra days. Looks like that. It's a hyperbola with a shifted axis, right? That's a little bit beyond the scope of this course, but not beyond the scope of your calculus sequence. So they'll bring that up and tell you how to shift axes and things like that. But that's why they're calling it hyperbola. You don't have to just take that at face value. So we're going to do substitution again, distribute the x, bring everything over to the right-hand side. And the reason is to get that x squared positive. That looks good. Factors of 1 that add to be 2. And so the only solution that comes out is a 1. We substitute that into the line and come up with a nice 1, 1. Just so you know what you're looking at, that's what you were looking at using a graphing utility. A circle and a parabola. Well, those could have a lot of points of intersection. Certainly could have 4, right? Could have just 2 if it's inside. 3 if one of the vertex points is on there. None, I guess, theoretically in there. 1 if the parabola is tangent to the circle in some way. So we don't know. We'll figure it out. So we are going to substitute y into x squared plus y minus x squared equals 4 in place of x squared. So let's see what they did. He's saying one thing but doing another, I think. The best substitution right now is to realize that x squared and this x squared could be substituted. You do not have to substitute for just a single variable. So take a look at this. Forget this line. I think it's misleading. Y equals x squared. Conversely, x squared is y. So what do we want to let this x squared be? Y. And come right down to here. Y plus y minus 2 squared is equal to 4. Y plus y squared minus 4y plus 4 is equal to 4. And then if we bring everything together, this makes the negative 3y that you see there, bringing the 4 over cancels them out, and then the y squared. And so we have 2 points of intersection, 0 and 3. So we're going to substitute those into the most simple one we can. You plug the 0 in, we get 0, 0. You plug the 3 in, don't forget your plus or minus. We get plus or minus, and so we get 3 1s, and this is one where the vertex point of the parabola is tangent to the circle, right? It's right on the same edge as the circle. And so that's how we're getting 3. And then an ellipse and a hyperbola. Okay, so a little bit crazy here. This is an example of where elimination might be the best. Substitution would be a killer. And so what are we going to do? We're going to take these two equations and we're going to modify them. We're going to multiply the first one by 3 and the second one by 2 so that we get rid of the y squared. So just like you did elimination in previous courses. We triple everything, including the constants at the end. We add, and we get 17x squared is equal to 153. If you divide by 17, you get a 9. And so we get two solutions, 3 or negative 3. Now we're going to substitute those into whichever one you feel is the easiest. I don't know how you'll make that determination. He chose the second one. I think they're equally as difficult. If you plug a x1 is equal to 3 in there, you get 9 times 4, 36, right? And then you just keep that process going, and you get a nice negative There's 4 out of that, and a plus or minus 2. So here's 2 solutions. And then if you use the negative 3, the same thing is going to work out because of the squared, but you'll have a different x value. And so there are 4 distinct points, and you can get a look at what that looks like right there. It's that baseball type of shape that I drew earlier. 2 more examples. Example 8. Again, I would use substitution just like he does. 2x plus 3 going in for the y's. And so we have a little bit of a problem here. So he has 2x plus 3 going in, but he's forgetting to square it. So this is not done right at all. So he treated it like it was y is equal to x squared plus 3x. Oh, you know what? He's calling it a parabola. So the mistake comes right here. Let's follow his work. There should not be a 2 there. It wasn't a parabola. With that y squared in there, it would have actually been a hyperbola, because the x squares and y squares, if I got them on the same side, would have been opposite signs. So let me erase. That should have been a y. And so now we're good. So that 2x plus 3 goes in there. We moved things over. He's trying to give you the realistic result that you could get this type of work right here. Now, he's going to allow you to use a calculator to come up with a decimal approximation of those. Fine. We plug those in and we get corresponding y values. Plug them into the line, right? The reason why we want to plug into the line is because it's 1 to 1. It has no squared values, so it wouldn't give us duplication. And then the last, I guess that was the last example. So he's just letting you know here that there's applications out there for all of this. The best part is the thinking aspect that's going through. And so it's good holistic math that you'll absolutely do again in future classes, and that's what this is bringing out, that most of the stuff that we deal with in sciences is nonlinear, and we care about intersections. So there you go. That's chapter 10 for you.